We've been doing circular functions for about a week now, and I'm sure none of you, or some of you, are none the wiser about why this graph looks like that. So why do we get this waveform? Well, ready to see something cool. What I've got here is a unit circle and a Cartesian plane sitting next to each other. And what you'll note here is that we've got theta, the angle on the unit circle, is 0 degrees. And what this is going to do is it's going to plot the y values as I move around this unit circle. So as I move this angle here, or this slider here, it's going to increase the angle, and it's going to continue to read out and plot the y values as we move around the unit circle, as theta increases. All right, and ultimately what we'll do is we'll stop when we get to 1 here, because the y value is going to be 1 after 90 degrees. So after 90 degrees, we're going to get a y value of 1. See what happens. Here we go. So you can see here 33, 34. What happens is the y values increase all the way to 1. Now what do you think will happen? Well, as I increase past 90 degrees, what will happen is the y values will decrease and go back down to 0. Okay, and it's going to be symmetrical because this is a circle. That's one of the cool things about circles, is it's going to go back down. So it should do that. Nearly gave it away there. Get back there, get back there. Yeah, all right. So now at 180 degrees, what do you think happens now? Okay, so what will happen is the y values here will start to go towards -1. So from 0 towards -1. So from 0, the y values are going to go down. Okay, and because again it's the same shape, we're going to get this sort of shape here, or this shape here, coming down here. So let's just see. All the way to 270. Okay, so we get that to there, and then if you can see, hopefully you know what's going to happen now, that this part here, the y values, if we track them, will increase back up to 360. And because this is a circle, I can just keep going around in a circle. If I tell you to start running around the circle, you're going to keep going indefinitely until I tell you to stop. Or of course you're going to whinge to me and tell me I'm not running around a circle, Mr. Miller, but don't say that because that sort of defeats the point of the story. So this would keep going along like this, but I also could reverse this up. So I could do -90, which would be here, which would actually be this part here and that part there. And so what we are going to end up generating is, where is it? Slide it back in again. It is that graph there. Okay, so we get that waveform, and it will just continue indefinitely. Okay, continue indefinitely in the negative or positive direction, unless of course it's got a restricted domain. Okay, so the graphs of y equals sine and cosine. So this is kind of like, I don't know, you want to consider its general form. Okay, so this a value here, what it represents is what we call the amplitude. Okay, and that is a dilation. Okay, so it's a dilation from the x-axis. So sine by default will have a maximum and minimum value of 1 and -1. And this a value here is going to affect that. Okay, this n value here, okay, this has got to do with what we call the period. That's how long it takes to repeat itself. Okay, this is theta plus b. This b here is a translation. Okay, and this will translate b units to the left as it stands. And this is a vertical translation. So this will be c units either up or down, in this case up. All right, so what we're going to do is just draw the basic y equals sine x, and then do the basic y equals cosine x. So for the basic sine and cosine graph, one complete cycle of function is 2 pi or 360. And why? Well, you'll note that it will repeat itself every 2 pi. So the period of the standard, so y equals sine x, the period of the standard sine x function is always going to be 2 pi. Now we can change the period. So this n value here is the thing that changes it, and what it represents is a dilation factor n from factor 1 on n from the y-axis. Okay, so to get the actual period of a function that we're dealing with, okay, we look at any coefficient here, and let's say for argument's sake that this is sine 2x. What that will be is, that will be at period change of 2 pi over the n value over the 2, which means that we've got a period of pi. Okay, so what that will do is just increase how quickly or how rapidly the function repeats itself. Okay, now the reason for that is that represents a dilation factor half from the y-axis. So what it will do is grab the normal y equals sine x function and chop every value by half. Okay, every x value by half, which essentially means it repeats itself. And I'll show you how that works in a graph. So into this function here, I'm going to drop x on 2. Okay, so that's dilating by a factor of a half. That was stupid. Wanted to dilate by a factor of 2. Let's get rid of that. So f of 2x, which represents a dilation factor half from y. And you notice there that what it does is it repeats itself after 3.1 or repeats itself after pi. Okay, whereas this one repeats itself at 6.4, 6.3, that's roughly 2 pi. Okay, so yeah, that's a dilation factor 1 on n from the y-axis. The domain is the set of all real numbers, and the range, okay, is, you can get it by doing c take away the amplitude and c plus the amplitude, but I'm not going to use that formula. I'm going to show you how it's done. All right, so let's graph y equals sine of theta. Okay, so the way we're going to do this is we're going to note that it is y equals 1 times the sine of theta. So the a value is 1. So we're going to say that the amplitude, that's a new word I know, is 1. Okay, I usually just write amp 1. Okay, a period is, for a standard sine function, is going to be 2 pi. We look for an n value here and divide 2 pi by the n value, which is 1, which is 2 pi. All right, now the last step we need to use or do to sketch these functions is we work out how we're going to mark our scaling. And the way we do that is we split 2 pi into 4 parts, okay? And you'll see why in a sec. So we're going to go 2 pi on 4, okay? So we split the period into 4 parts, which is pi on 2. So when we mark in our scale here, we're going to mark it in at an interval of pi on 2. So there's pi on 2, there's pi, there's 3 pi on 2, and there's 2 pi. All right, so how does sine work? Well, at 0, sine of 0, wonder what it is. There it is there. What's the y value at 0? It's going to be 0 as well. At pi on 2, or 90 degrees, what's the value of sine? It's equal to 1. So it jumps up to there. Over here, goes back down to 0. Down to here, goes down to -1. And back to where we started. Right, so what do you think happens in between? Well, we get this beautiful, whoa, that's not beautiful. Beautiful waveform function. Oh, that's shocking. Okay, can you please make sure that your graph is nicely smoothed out? None of that, none of that. Okay, again, my excuse all through this remote learning period is that this pad is dodgy. Okay, right, and what will happen, girls, is that will continue indefinitely for all values of x, unless it's got a restricted domain. All right, well, cosine. Let's do cosine now. Doesn't say we have to do cosine, but I presume, yeah. So this is, it's y equals sine of x, and this is y equals cosine of theta or x or whatever. Okay, so how does the cosine graph work? Well, it works exactly the same way as the sine graph works. What we're going to do is note that it's y equals 1 times the cosine of theta. Our a value is 1, therefore our amp is 1. Our period for a standard cosine graph is 2 pi divided by the n value, which is 1. So our period is 2 pi. Our scale will be 2 pi on 4, which we already established is pi on 2. Well, let's mark our scale. Pi on 2, pi, 3 pi on 2, and 2 pi. Okay, so we've got amplitude of 1 and -1, or amplitude of 1, which means it goes up to 1, down to -1. All right, so what's different? Well, let's plot the unit circle, or not plot, but do the unit circle and find out. All right, so here at 0, what's the cosine? Well, that's the x value there, and that's going to be 1. We go up to 90, okay, or pi on 2, and we note that the x value is 0. We swing all the way down here, and we note that it's -1, back to 0, back to 1. Okay, so the cosine graph is exactly the same as the sine graph, except it's just moved slightly to the left or right, depending on which way you want to transform it. Okay, so just note a couple of things, that is a turning point there, so you don't cut in too sharp. Okay, see, students just head straight for that turning point and make a sudden turn there. So it should look a little bit like a bowl. Okay, remember that continues for all values of x. So essentially all this is a sine function moved pi on 2 to the left. Okay, so if I move the sine function pi on 2 to the left, I can actually generate the cosine function. The way I think about it, sine by default starts at the origin, cosine starts at 1, or I, in my mind, think cosine starts high. Okay, so starts high and spills out. Okay, whereas sine starts at 0 and goes up from there. Okay, so our A value is max take away min divided by 2. Right, so you take your maximum and your minimum. Okay, so that's 2. 2 divided by 2 is 1. So our amplitude is given by this, but I'm going to teach you a way to not worry about this formula here. Okay, this C value is the vertical translation, is the max plus the min, which is 1 plus -1, which is 0. 0 divided by 2 is 2. That means it has not been vertically translated. Okay. Right, so sketch a graph of the following functions, labeling the coordinates of all axial intercepts, turning points, and endpoints. All right, here we go. So we've got y equals 2 sine 3x. So our amplitude is going to be 2. That means its maximum and minimum value without any vertical translation is going to be 2 and -2 respectively. Right, our n value, we do have one this time. So our period for a standard sine function is going to be 2 pi, and what we do is we divide it by this value here, what we call the n value. So that's 2 pi on 3. All right, so what I'm going to do then is consider my scale. That's 2 pi on 3, okay, and I'm going to split the period 4 separate ways. Okay, so what we do when we split it 4 ways is we basically just multiply the denominator by 4, which is 2 pi on 12, or pi on 6. All right, so here's the domain over which we have to sketch it over. So we can rule this up like so. All right, and now what we're going to do is mark in our scale. Okay, so my advice is to actually use the fraction version that hasn't been simplified and write the simplified version underneath it. Okay, so we're going to note that this is 2 pi on 12, which is pi on 6, 4 pi on 12, which is 2 pi on 6, which is pi on 3. Oh my god. Okay, that is going to be 6 pi on 12, which is pi on 2. And this is going to be 8 pi on 12, which is 2 pi on 3, which actually happens to be the period. Okay, so they want this to go to 2 pi. They want it to go to 2 pi. So yeah, that's a problem. Okay, that's a problem. We're going to get away with this. We're going to change this. Okay, so we're going to go 10 pi on 12, and that is going to be 5 pi on 6. And we're going to scrap the 2 pi and write this as 5 pi on 6. Okay, so that's the domain over which we want to do this. All right, let's get this sketch going. So it's a sine function. So sine functions without a vertical translation will start at the origin. And let's mark in our -2 and our 2. Right, so what it's going to do is it's going to go up to 2. Now, it usually goes up to 1, but that 1 gets multiplied by the 2 to make it go up to 2. So it's like, again, a dilation factor 2 from the x-axis. It would usually go to 1, gets multiplied by 2, dilated by a factor of 2 from x. Okay, so it starts up there, down, goes down to here, up to there, and back up again. Okay, so sine will just follow that basic procedure. So it starts at the origin, up, down, down, up, up. All right, so now all you have to do is just draw a nice smooth looking curve, connecting the dots, like so. Okay, that's bad, but the rest of it looks all right. Okay, what does it say? Sketch the graph of the following functions, labeling the coordinates of all axial intercepts, turning points, and endpoints. So here we go. We've got the origin, which is also the y-intercept, pi on 6, 2, pi on 3, 0, of course. This one here is pi on 3, pi on 2 rather. This one here is 2 pi on 3, 0, and finally 5 pi on 6, 2. That one's wrong. That should be pi on 2, -2. Wow, really stuffed that up. Okay. All right, so there are the turning points. I've got an x-intercept there, x-intercept marked, endpoints are marked. Defined at the endpoints, yep, all good. Okay, so there's my sketch. Now the reason I didn't go to 2 pi here was that I already set my scale early. I just didn't want to, if you're following the video and set your scale, I didn't want to make you guys get out your rubber, erase it all so that we can extend it out to 2 pi. Right, but we'll get the next one right. So this is f of x equals -3 sine 2x. Right, so let's do the kind of grunt work first, as I call it, the amplitude. Now you might be tempted to write 3 here, -3 rather, but the amplitude in fact is 3. So it's always the positive amount. We call that the absolute value, which means it's always positive. All right, now what does the negative do? Well, maybe you're thinking it might reflect it in the x-axis, and if you think that, you'd be 100% right. Okay, so the usual sine function will go up and down like that. This one here will go down and then up. Okay, it will reflect in the x-axis. Right, so we just need to remember that when we sketch it. Now, amplitude is 3. Period for a standard sine graph is 2 pi. And what we're going to do is divide it by the n value, divide it by that value there, which means the period is pi. All right, how are we going to mark our scale? So our scale will be the period split into 4 parts. So our scale is going to be pi on 4. Now we're ready to go. Okay, so I'm going to go -3 and 3 there. Okay, make sure that they're roughly the same distance. Don't measure it or anything, but okay, so we need to send this out to 2 pi. So here is pi on 2, pi on 4 rather. 2 pi on 4, which is pi on 2. 3 pi on 4. 4 pi on 4, which is pi. 5 pi on 4. 6 pi on 4, which is 3 pi on 2. And 7 pi on 4. 8 pi on 4, which is 2 pi. Right, make sure that they're roughly the same distance. If you did use the unsimplified version of the fraction, you need to write the most simplified version on the scale. But again, if you do that, I agree, it makes it really easy to write your scale in if you use the unsimplified version. All right, so here we go. So sine will start at the origin if it's not vertically translated, which it isn't. And then it would usually go up. But what this one will do is because of the reflection, it's going to go down. So it's just going to go in opposite direction that it usually would. So all I do is I get my key points in there and then just draw a nice smooth curve, linking all of them up. Okay, so if log graphs were difficult to do with this pad thing here, trig functions are excruciatingly difficult to be nice and smooth. So that is, what would I give this? This is like 0% good. Okay, that is the world's worst graph. Fed income, that is like, don't show your parents this. Okay, don't show tutors this. Okay, that is the world's worst graph. This curve should be nice and smooth. Okay, so no excuses, girls. I've shown you how low the bar can go. You've got to go better than that. Okay, that will be passed around VCAR if you supply that, or I showed my mates that. That'll be supplied with the attached note saying world's worst graph. Okay, so can't overstate it enough that I'm not trying to say that this is acceptable in any way other than the only way I can sketch these things and record this video. Okay, let's have a little go at this one here. Okay, so what do we got here? We've got an amplitude of 3. Our period for a standard sine function is 2 pi over the n value, which is 2, which is pi. Our scale is going to be pi on 4. Okay, so it's the period split 4 ways. And this -3 is going to lower the function. Okay, so let's just see how that's going to look. Right, so draw up my Cartesian plane. What I'm going to do is draw this one a little bit differently. Okay, now, right, so what do I know? I know that this value here translates the standard sine function, which will start at 0, 0, and send it down 3 units. So it's actually going to start there. And that we're going to call -3. So it's going to start there and jump. How high is it going to jump? Well, that's the amplitude. It's going to go up 3 units. So it's going to go up to the origin, and it's going to go down another 3 units to -6. So it's going to go and do its thing there. All right, let's label our Cartesian plane again. So pi on 4, pi on 2, 3 pi on 4. I'm just copying the labeling from above. Pi, 5 pi on 4, 6 pi on 4, which is 3 pi on 2, 7 pi on 4, 2 pi. Why did I put that there? That looks terrible. Pi on 4. Okay, so here goes. All right, now what sine functions do is they typically start at 0, 0, translated 3 units down. It's going to start there. It's not reflected, so it's going to go up, down, down, up, up, down, down, up. Okay, here we go. Oh. Not as bad as the other one, but what is that? All right, anyway, here we go. So I forgot, I was just critiquing my previous graph so much that I forgot to put in the key features. So turning points, pi on 4, comma, -3, pi on 2, comma, 0, origin, because that is the y-intercept, 3 pi on 4. It's pretty arduous, this, especially if you get a lot of repetitions over the domain. 3 pi, comma, 0, 5 pi on 4, comma, what's that one? -3, etc., etc. Can you please label the rest of them, making sure that you label the endpoint, which is also an axis intercept. Okay, so same over here with this one. That's going to be 0, comma, -3, pi on 4, comma, 0. That one is not a key point. This one here is 3 pi on 4, comma, -6. This one's the next one, 5 pi on 4, comma, 0, etc., etc. Can you please make sure that you label the rest of them, including the endpoint, which is 2 pi, comma, -3. Okay, I think we'll leave it at this one for the last one that we'll do, and we'll leave out translations just for the moment. So we want a cosine graph here. So let's just do some of the legwork. Amp is going to be 1, period, for a standard cosine function is 2 pi over 2, which is pi, okay, where that is the n value. Okay, now scale. Getting a bit boring here, isn't it? Pi on 4, it's the same again. We're going to note that this 2 translates or sends the standard cosine function up 2 units. Okay, let's get sketching. So for this one here, what I'll do is I'm going to put my Cartesian plane together. I'm just going to draw that horizontal axis a little lower. Okay, 0 to 2 pi. Okay, let's get cracking. So what I usually do is mark out my key features. So it's going to start, so here's 1, here's 2, and it's going to go up 1 more to 3. So it's from 2, it's going to go up to 3 and down to 1. Okay, so that's how this one is going to play, given that it's got an amplitude of 1. Okay, let's mark in our scale. So it's got pi on 4, 2 pi on 4, which is pi on 2, 3 pi on 4, 4 pi on 4, which is pi, 5 pi on 4, 6 pi on 4, which is 3 pi on 2, 7 pi on 4, almost there, and 2 pi. Okay, so remember what we're dealing with now. We're dealing with cosine, and cosine starts high and goes low. So cosine would typically start at 1, okay, but this translation 2 units up is going to mean that it starts at 3. Right, so what happens is cosine spills from high, like a bit of a waterfall, that's how I imagine it anyway, down to the what we call mean line, or the translation line, so it goes up 2 units. Then down to here, back up to here, back up to there. Draw these dots in before you actually sketch the function, because it becomes a bit like a join the dots thing, which is kind of fun. All right, let's see how badly I can do. Now remember, don't go too like straight down there. Okay, what happens is it spills over the edge like a waterfall. My apologies. No. I'm running out of pad space here. That's why I can't get up there and there. Okay, again, that's pretty abysmal. Okay, again, my apologies. 0, 3, pi on 2, comma 1, pi, comma, what's that? 3. 3 pi on 2, comma 1, and 2 pi, comma 3. Back up there again. Okay, so there are a number of sketches there. Okay, it takes time to sketch trig functions. You should take your time sketching them. So what have we done? 1, 2, 3, 4 graphs. Video's gone for 28 minutes. Okay, so yeah, like don't rush these. They do take time.